Thanks, Nicole. I'm glad to have the opportunity to talk about our work with Isaac Kim and Eugene Tang on the ghost in the radiation. This work concerns an issue that has puzzled physicists for decades, namely how black holes process quantum information. And there's actually been substantial progress recently in understanding these issues, where concepts from computer science have really been crucially important for guiding our progress. Concepts like computational complexity, pseudo-randomness, and error-correcting codes. These are all concepts developed in the context of classical computing, but they are enriched when viewed from the perspective of quantum physics. I actually had a chance to speak at STOC 4 years ago about the related topic of what error correction has to do with the structure of space-time. And since that report 4 years ago, a lot has happened. There's really been a lot of progress. Very little of that is due to my own work. But what has happened is we now know how to do quantitative computations that provide a firmer foundation for some of the ideas we've been speculating about for a while. From the standards of theoretical computer science, these foundations are a bit heuristic, not really based on a fully rigorous understanding. But the upshot can be summarized by saying that the evidence is accumulating that space-time is not really fundamental in physics. It emerges from some deeper description of nature that we still don't understand very well, that it's actually possible to break space apart into pieces. And what prevents that from happening is that it requires a computation of super polynomial complexity. We have a very beautiful theory of classical gravitation, general relativity. It says that space-time is a Riemannian manifold, that in the absence of other forces, objects move along geodesics, and that the curvature of that manifold is determined by energy and momentum. But we'd like to combine this theory of gravitation with quantum physics, and it's been challenging to do that. So why is that important? Well, we're physicists, so of course we want to have as complete an understanding of fundamental interactions as we can. And we hope a better grasp of quantum gravity will help us to resolve deep puzzles about quantum black holes, which I'll discuss. It may also help us to understand what was happening in the very early universe right after the Big Bang. And importantly, I think we can expect that if we arrive at a deeper understanding of quantum gravity, that will teach us lessons that are more broadly applicable to other areas of physics. But it's been difficult to make progress on quantum gravity. And one of the major obstacles is we're getting very little guidance from experiment. The situations in which quantum gravity has significant effects are very exotic and elusive, hard to explore in laboratory experiments, and that's how physics usually makes progress. In this case, we're trying to figure things out without that guidance from experiment. Are we smart enough to understand quantum gravity? I don't know, but maybe we are, so we should certainly try. Now, a black hole is a really marvelous object. From the perspective of classical general relativity, it's remarkably simple. It's composed of nothing but pure warped space-time geometry. The defining property of a black hole is that if you foolishly cross the event horizon and enter a black hole, you'll never be able to return to the outside or to communicate with your friends who stay outside. We can envision the geometry of the black hole by thinking about the light cone. The forward light cone of a point in space-time contains all of the events that can be influenced by something that happens at that point. And as you approach the event horizon of a black hole, the light cones tilt inward. So once you're inside the black hole, you can't avoid going more deeply into the black hole until finally you encounter, at least according to classical theory, a singularity where enormous gravitational forces tear you apart. It's really not pretty. Now, we do know one thing about quantum black holes. We've known it for a long time, thanks to Stephen Hawking. They're not really black. They can emit radiation due to quantum effects. And that radiation really results from quantum entanglement, from quantum correlations between the interior of the black hole and the exterior. If we're limited to observing things from outside the black hole, we're seeing only part of a quantum state, and the result is that that state looks mixed, like there's missing information. In fact, according to semi-classical theory, it's a completely featureless thermal state, revealing no information about how the black hole formed, with a characteristic temperature such that the wavelength of the radiation is comparable to the size of the black hole. So that means we can consider the disturbing scenario in which we encode some information in the quantum state of some matter, allow that matter to undergo gravitational collapse to form a black hole, which then begins to emit Hawking radiation. And after a suitably long time, it radiates away all of its mass and disappears. Now, other objects which emit thermal radiation, we think, although a process looks thermodynamically irreversible, microscopically it's reversible. In principle, we could run it backwards. But black holes seem to be different because of the event horizon. At first blush, it appears that a process like this one would destroy information. That information would be removed from the universe, and the process would not be microscopically reversible. And that's really a big deal, because if true, it means that we need to recast the foundations of quantum theory. But we might take the attitude that black holes aren't really fundamentally different from other objects, that the process of a black hole forming and evaporating really is microscopically reversible. The black hole, like other thermal objects, scrambles up information, so it becomes very hard to read, but doesn't really destroy it. And we'd like to reconcile that belief, if true, with other things that are very natural to believe. For example, that an observer who falls through the black hole horizon doesn't notice anything unusual at the time of horizon crossing, though later on that observer will be destroyed at the singularity. This is what classical gravitation theory predicts. And also that an observer who stays outside the black hole sees no surprising violations of the usual rules of local quantum physics. But it's been argued that it's very hard for these three reasonable beliefs to all be reconciled. And it's even been suggested that to resolve the tension, one should give up on option 2, so that an observer who reaches the horizon does not pass through unscathed, but is actually immediately destroyed in a seething firewall due to quantum effects, something very different than what happens in the classical theory of black holes. So why would one believe something so crazy as the existence of a firewall at the black hole horizon? It's because of a fundamental difference between classical and quantum correlations. In classical information, correlations are what we call polyamorous, or we could call polyamorous. That means they can be shared by many parties. Betty and Adam could read the same newspaper, so they have shared information and they become correlated with one another. But there's nothing to prevent Edward from reading that same newspaper, and then he's just as strongly correlated with Betty and with Adam as Adam and Betty are with one another. But quantum correlations are different. They are harder to share. They are monogamous. If Adam and Betty have the strongest possible quantum correlations, if they are fully entangled with one another, that means Betty has used up all of her ability to entangle with Adam and can't be correlated with Edward at all. And on the other hand, if Betty is fully entangled with Edward, then she can't be correlated with Adam at all. And so that monogamy of entanglement can be frustrating. Betty might want to become more entangled with Edward, but she could do so only by sacrificing some of her entanglement with Adam. And that fundamentally quantum feature of correlations, the monogamy, is at the core of how we can use quantum states for secure communication, how we can understand the entangled phases of quantum matter, And it's also important in black hole physics. And here's why. Suppose we consider an old black hole that's been evaporating for a long time, and it has been revealing information about its origins, about the object from which it originally formed due to gravitational collapse. So what that means is that the Hawking radiation that's being emitted now is becoming entangled with radiation that was emitted a long time ago, because the information is being reassembled outside the horizon. But if it's also the case that a freely falling observer who crosses the horizon notices nothing unusual, then that means there must be entanglement between this recently emitted radiation and degrees of freedom behind the horizon. And if the physics outside the black hole is the normal local quantum physics that we know about, then if system B is entangled with system E, once it pulls away from the black hole, it must already be entangled with E at the time that it's first revealed outside the horizon. So now we have a conflict because system B wants to be highly entangled with system A so that an observer crossing the horizon doesn't see anything unusual. But system B also wants to be highly entangled with system E so that the information is revealed as the black hole evaporates. So one way of resolving the tension would be to break the entanglement between B and A, but that would give rise to a firewall at the black hole horizon. It would mean that unlike the vacuum, there would be energy concentrated at the horizon, which would be encountered by that freely falling observer. So how are we to resolve the tension? The emerging consensus is that, in fact, it is possible for system B to be entangled with both system A and system E because system A is not really an independent system. We can think of the interior of the black hole as being encoded through a very complex encoding map in the radiation that was emitted a long time ago by the black hole. Now, that's a very crazy proposal because it's wildly non-local. It means that Edward, who's interacting with that early radiation, which might be light years away from the black hole, can touch Adam, who's inside the black hole. Well, yes, according to this proposal, in principle, that's possible. But the claim is that in order to interact with Adam by interacting with the radiation, Edward would have to perform an operation of infeasible complexity, with complexity which is super polynomial in the size of the remaining black hole. So Adam, the encoded interior, is actually surrounding Edward, but he can't interact with Adam. Adam is the ghost in the radiation. So in our work, we considered this setting. A black hole forms through some efficient process described by a unitary transformation, which takes the infalling matter to a state with three parts: E, the early emitted radiation; H, the remaining black hole; and B, the recently emitted Hawking radiation. And that system B is highly entangled with some subsystem of E and H, and we want to interpret that subsystem that B is entangled with as the black hole interior. Now, some observer comes along, O, and interacts in a computationally bounded way with the early radiation. And what we want to claim is that the observer O is unable to influence that encoded interior and unable to break the entanglement between system B and the encoded interior. And in order to draw that conclusion, we need to make an assumption. And our key assumption is that the Hawking radiation is pseudo-random. So what I mean is that after a black hole has been evaporating for a long time, the information about how it formed is being revealed in the Hawking radiation and in principle can be decoded. But in order to do so, we would have to do a computation of super polynomial complexity. To any observer who does a computation whose complexity is polynomial in the size of the remaining black hole, the radiation is virtually indistinguishable from purely thermal featureless radiation, just as Hawking originally envisioned when he computed the properties of Hawking radiation. The information is there, but it's very hard to extract the information. So should we believe that this efficient process in which the black hole produces the outgoing radiation can prepare such a pseudo-random state? Well, we do know from, if we accept assumptions of post-quantum cryptography, which our future privacy will be founded on, namely the existence of injective one-way functions that can't be efficiently inverted by a quantum computer, then such pseudo-random states exist, which can be efficiently prepared. And our attitude is that black holes are such vigorous scramblers of quantum information that if such states are possible, if such efficient processes exist, then a black hole will be able to do it. And our main result is that if the observer is limited to operations of polynomial complexity, then we can construct an algebra of operators which act on the encoded interior embedded in the system EH, such that any action taken by that computationally bounded observer very nearly commutes with the ghost logical operator. So the observer is not able to interact with or influence the encoded interior, and so causality is satisfied. The inability to interact over vast distances is satisfied if we limit ourselves to observers of realistic complexity. So the technical part of what we do is use the theory of approximate quantum error correction to show that the construction of the ghost logical operators is possible if we make that pseudo-randomness assumption. We have this highly entangled state in which B is nearly fully entangled with some subsystem of EH. We can think of that state as defining an approximate isometry, which takes the encoded interior into EH and regard that as the encoding map of a quantum error correcting code. And then from the pseudo-randomness assumption, it follows that if O is computationally bounded, limited to operations of polynomial complexity, then O is nearly uncorrelated with system B. So that means that O isn't really interacting with the encoded space in EH, which is entangled with B. And that means that if we regard that encoded interior as a quantum error correcting code, that the operations performed by the computationally bounded observer are correctable by some suitable recovery map. And then what we can show is that because of that correctability, we can extend the logical operators acting on the code space to the larger space of all states that can be reached by the correctable operations performed by O. And that gives us this algebra of ghost operators, which nearly commute with all the operations performed by the computationally bounded observer O. Now, usually in quantum error correction, we're interested in protecting a quantum computer from noise so we can do scalable quantum computing. And under those circumstances, we consider the noise to be fairly benign, as we hope it will be in an actual device, reasonably weak and not too strongly correlated. The setting we have here is quite different. The observer O is allowed to do anything he wants, subject to the computational complexity restriction, so the noise can be highly correlated and chosen adversarially. Nevertheless, we were able to identify a code space which is protected against that noise inflicted by the observer. And what makes that possible is that the observer does not interact with the remaining black hole degrees of freedom. The system H acts as the key space for our pseudo-random state. And so H is noiseless, even though E is handled very harshly by the noise. And that's what makes it possible to have a robust system embedded in EH, which can't be damaged by the computationally bounded observer O. So to sum up, physicists often speak of effective quantum field theory as a good approximation to physics, not an exact description, but a good approximation to physics if we consider energies which are not too high, and space-time curvatures which are not too high. But there's an additional tacit assumption that's needed for our usual description of local quantum physics to apply, namely that we limit to operations of sufficiently low computational complexity. If we consider an information theoretic setting and don't worry about complexity, then high complexity operations can actually tear space-time apart, and the semi-classical picture of causality no longer applies. Now, in our work, we just show that encodings with the properties that I described for the black hole interior exist. We didn't show that that's what would really happen if an observer falls into a black hole. There are explicit computations, which we had nothing to do with, performed by others, that provide support for the hypothesis that the interior of an old black hole really is encoded in the Hawking radiation that was emitted much earlier. But those computations haven't provided us with a very satisfying understanding of the mechanism by which the information escapes. So we're hoping that with further progress, we can get a deeper understanding of just how information can get out of a black hole. And as we learn more, hopefully, we'll have a good enough grasp of quantum gravity to be able to make sharper statements about what was happening in the early universe right after the Big Bang. So as I've emphasized, these recent insights have relied heavily on ideas from theoretical computer science. And I think that will continue to be true as we make progress in the future. So thanks for listening to me, and thanks for those great ideas.